In the diagram, the square EFGH is centered inside a square ABCD, and the region between the two squares is shaded. Determine the area of the shaded region if the length AB is 10 and the length of EF is 8. So we have the big square, which is 10 squared, minus the little square, which is 8 squared, so that would be 36. Part B, determine the length EF if the length of AB is 13 and the area is 120. So a little bit different this time. This is 13 squared now. The EF, I guess we have to figure that out. EF squared, and they're telling us that's 120. So that's 169 minus 120, which is 49. And that's EF squared, so EF would be 7. Determine the length EF if the length AB is 18 and the area of the shaded region is 3/4 the area of ABCD. Alright, so a little bit different this time. This would be that the area of the shaded region, AS, is 3/4 of ABCD. Okay, so then the AS would be 18 squared minus EF squared, I guess. And that is 3/4 times 18 squared. And that would be 324 minus EF squared is 243. And therefore EF squared would be 81, and therefore EF this time is 9. Suppose that the area of the shaded region is 64% of the area of ABCD if the length AB is A and the length of EF is B. Determine the value of A over B. So this time it would be the area of the shaded region is 0.64 ABCD, and then that is going to be A squared plus minus B squared. Very similar to before, and this is 0.64 times A squared. And then that's going to be 0.36. A squared is B squared. A squared over B squared would be 1 over 0.36. And then therefore A over B would be the square root of 1 over 0.36. And this actually works out to be 5 over 3. For a 4-digit positive integer ABCD, where A, B, C, and D are digits, with A not equal to 0 and D not equal to 0, we define the reverse digit sum, RD sum, of ABCD to be the sum of ABCD and DCBA. For example, the RD sum of 1205 would be 1205 plus 5021, which is 6226, while the integer 2300 does not have an RD sum. Note that the 4-digit positive integer ABCD is equal to 1000A plus 100B plus 10C plus D. Determine the RD sum of 4281. 4281 RD sum would be that plus its reverse, which is 1824. And when you add those up, it's 6105. There are positive integers m and n with the property that a RD sum of integer ABCD is always equal to m times A plus D plus n times B plus C. State the value of m and n. Well, A, B, C, D plus D, C, B, A would be, according to what they're saying, m times A plus D and n times B plus C. So let's expand this. The first guy is, they actually help you out a little bit here, right? I think they gave you that for a purpose. So let's just put it in. Since they've given it, I'm sure they want you to use it. And then very similarly, this guy would be 1000D plus 100C plus 10B plus D. And this is the same. I'll just put that for now. And then when you add these guys up, it becomes 1000 and... Hold on, did I do this right? I think this is an A here. 1001A plus 110B plus 110C plus 1001D. And that's the same. And then now we can factor 1001 A plus D and then 110 B plus C. Yeah. And then now let's place that back. M times A plus D and n times A B plus C. Now if you compare both sides, I think you can clearly see that m is equal to 1001 and that n is equal to 110. Determine the number of 4-digit integers where the RD sum is 3883. So this time, since I've got this, actually it's this one I like to use, this one right here. Since I've already done all the hard work, let's just use it. So this is basically the RD sum of an integer of the form a, b, c, d. So they're saying that is equal to 3883. And what do they want? How many of them? Okay. All right, so we got to count. So there's obviously many. So let's start with that guy. A plus d, can it equal 4? I don't think so, because if it equals 4, then immediately this would be 4004, and that's greater than this. And this is positive, so that's going to be greater than. So it's not going to be 4. Can it equal 3? Yes. Can it equal 2? Yes. Can it equal 1, though? Let me think about this. A and D represent digits, right? And both of them cannot be, neither of them can be 0. That was very important, right here. A cannot be 0 and D cannot be 0. So the lowest that A and D could be is 1. So 1 plus 1 will be 2. So the lowest it could be at 2 is 2, so it cannot be 1. So the only values we have for A plus D is 3 and 2. Okay. So let's work with that. Let's make A plus D equal 2, or A plus D equal 3, and let's see what happens. Okay, so the first one, if A plus D is 2, let's plug that into here. So that's going to be 2002 plus 110 plus B plus C is 3883. So this would be 1110. B plus C is 1881. And therefore B plus C would be 17.1. Okay, well that falls apart immediately because B plus C has to be an integer because B and C are both integers. Okay, so that one's out. So I guess this is the only thing that most likely will work. So let's go with that. Again, plug it into there. So it's going to be 3003 plus 110 B plus C is 3883. And then this would be 110 B plus C, and that would be 880. And then B plus C looks to me like 8. Okay, that's great. So we've got that, and we've got this, and then I guess we have to just make a table here. So we have A, D, B, and C. And then let's see how many different... yeah, there's going to be a lot. But hopefully there's a quick way. So if A plus D is 3, the only possibilities are 1 and 2, or 2 and 1, because neither of them can be 0, right? Okay, so those two are fixed. Now B plus C is 8, so that and B plus C, interestingly, can be 0 because those are the middle guys, right? So B could be anything from 0 to 9, and C can be anything from 0 to 9. So you could have 0 and 8, 1 and 7, 2 and 6, 3 and 5. What else? 4 and 4. I'm continuing on that side, actually. 5 and 3, 6 and 2, 7 and 1, and 8 and 0. And the same story holds true here. So how many did I get? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it'd be 9 here. So 9 here, 9 there, total of 18. And you can list them all. And I encourage you to list them. So for example, I'll just list the first few. A, B, C, D, using this and this would be 1082. And then A, B, C, D using this and this would be 1172, and then so on. So I think you should probably list all 18. The positive integers are written into rows so that row n includes every integer m with the following properties. M is a multiple of n, m is less than or equal to n squared, and m is not in an earlier row. The table below shows the first 6 rows. Determine the smallest row in row 10. All right, let's first see if we can understand this question, and then we'll go ahead and make row 7, 8, 9, and 10, and then we'll see what is the smallest digit in row 10. Okay, so let's first try to understand the question. So this row is the n, and these numbers are m, I believe. So m is a multiple of n. So for example, if row 3, these, as you can see, those numbers are multiples of 3. 3, 6, 9, and so on. M is less than n squared. So you stop listing when you get up to n squared. So for example, it was 3. N squared would be 9. So that's why we stopped at 9. We didn't keep going. We didn't write a 12 and a 15. And m is not in an earlier row. I got it. So that means that, well, for example, in row 4, you should have written a 4 in there, right? But the reason you didn't is because it's in an earlier row. So if it's in an earlier row, you don't include it. So that's basically the rules, and let's see if we can fill these in. So for 7, I'm just going to put in all the multiples, and then I'm going to see if I can get rid of any that are in a previous row. And are any of these in a previous row? I don't think so. I don't see any. Okay, let's keep going. So for 8, it would be 8, 16, 24, 32, 40, 48, 56, and 64. Now, some of these are in a previous row, like 8 is, right? So I can't include that because, see, there's an 8 there. The 16 is also here. Can't include that. 24 is here, so I can't include that. I think everything else stays for now. And then 9, 9, 18, 27, 36, 45, 54, 63, 72, and 81. Now, how many of these are going to be gone? There's a 9 here, so I got to get rid of that because it cannot be. All the numbers can't be in an earlier row. M is not in an earlier row. Are the only ones you can include. So let's see, is 18 in an earlier row? It is, so that one leaves. 27, where's 27? No, 27's fine. 36, however, that's in an earlier row, so those are gone. And then 10, finally 10. Got 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, 10 is here, so that's gone. 20, I'm pretty sure there was a 20 somewhere. Oh, there's 20. 30, I saw 30 somewhere. Oh, here's 30. 40 is here, actually, so that goes. 50 is nowhere in a previous row. So that is the smallest integer in row 10. Okay, so all that hard work for that. Show that for all positive integers n greater than 3, row n includes each of n squared minus n and n squared minus 2n. So basically what they're saying is that if you have a row, like if this continued and you have a row n, that these two integers are going to be in that row. Now, where, how many others, that we don't know, but they're just saying prove that n squared minus 2n, which is this guy, and n squared minus n will be in row n if n is greater than or equal to 3. Okay, so n is greater than or equal to 3, so that means we started with 3, and then we kind of went up. Okay, let me start at the other end. We have n is the largest, and then n minus 1, and then n minus 2. These are the rows, correct? Yeah. Okay. Let's see if we can first prove this guy, and then I'll turn to the other guy. So n squared minus n. I have to show that this is in row n. So I guess I have to show that it fulfills these 3 criteria. Okay. So let's see if I can do that. N squared minus n. First of all, I can factor it to n times n minus 1. And this is in row n if it is not in a previous row. See, the first criteria is already fulfilled. M is a multiple of n. See, this is a multiple of n. It's n minus 1 times n. So that criteria is filled. Let me just write that here. So n squared minus n, which is n minus 1, is a multiple of n. Okay. Yeah, that was the first criteria. Now, is it less than n squared? Is n squared minus n less than or equal to n squared? Well, it is, because n is greater than or equal to 3. So if you subtracted it from n, it would be definitely greater than, less than n squared. So that's those two. Now the third one is that n squared minus n is not in a previous row, right? Is not in an earlier row. Yeah, we have to, that's what we have to show. Is not in an earlier row. If I can do that, then I will have fulfilled all three criteria. Okay, so that's what I have to concentrate on. Now, how do I do that? Well, let's see here. The previous row, the very previous, is n minus 1, row n minus 1. Now, since n is greater than n minus 1, obviously, if I multiplied by n minus 1 on both sides here, then that inequality still holds. So that means that n times n minus 1 is greater than n minus 1 squared. So that basically means that this guy, n times n minus 1, which is basically our n squared minus n, our main number that we're trying to figure out if it's in row n, is greater than n minus 1 squared. So that basically means that n squared minus n, which is equal to n times n minus 1, is too large to be in row n minus 1, because everything in n minus 1 has to be a less than or equal to n minus 1 squared, right? According to that rule. So our guy is too large to be in row n minus 1, since it's greater than n minus 1 squared. So that's very important. And if that's the case, then n squared minus 1 would also be too large to be in any of the other rows, to be in any of the other previous rows, like n minus 2, row n minus 2, row n minus 3, and so on. Because n squared minus n would be obviously greater than n minus 2 squared. Since it's greater than n minus 1 squared, it will be greater than n minus 2 squared. Okay, so that proves point number 3, that n times n squared minus n is not in any earlier row. So it's a multiple, it's less than n squared, and it's not in any previous row. Okay, perfect. So we got all three for this guy, for this one. Okay, so now we've got to do the same thing, but this time for this one, n squared minus 2n. So very similar. Very similar, I guess. Hopefully not too complicated. But this time, we've got to show it for n squared minus 2n. We've got to show these three things. That it's, well, the first one's easy. N times n minus 2. Well, there we go. That proves that it's a multiple of n is a multiple of n. Okay, so that one's done very quickly. Then we have to show that n squared minus 2n is less than or equal to n squared. Well, that is done. Immediately we know that's true, since n is a positive number greater than 3. So when you subtract it from n squared, it's going to be less than. So that's done. So now we have to show this part, that n squared minus 2n is not in an earlier row. Okay, that is the part I have to show. Okay, so the earlier row, let's start with n minus 1. Yeah, so row n minus 1. So what we have here is a row n minus 1. If you squared it, it would be n minus 1 times n minus 1, right? So that's n squared minus 2n plus 1. And therefore, if we were to take this and modify it a little bit, it would be n squared minus 2n on one side. And then n minus 1 squared minus 1 if you put the minus 1 over. So since the n is greater than or equal to 3, that basically means that that n squared minus 2n and the n minus 1 squared, it looks like they differ by 1, right, according to this. And if they differ by 1, then n squared minus 2n is not a multiple of n minus 1. Let me see here. Yeah. Therefore n squared minus 2n is not in row n minus 1. Okay, but we've only showed this for row n minus 1. There's n minus 2, n minus 3. There's got to be a faster way, right? You can't do this every row at a time. So let's see what happens if I do it generally, what I did up there, very similar to what I did up here, right here. Hopefully that will help for other rows. So we have this n squared minus 2n, and that is n times n minus 2. So that is going to be greater than n minus 2 times n minus 2, right? Because that's greater than that. And then that's n minus 2 squared. So that means this, because it's greater, that means that this is too large to be in row n minus 2. Yeah, and therefore n squared minus 2n is too large to be in any row, n minus 3, n minus 4, and so on. Yeah, because of that rule that it's got to be this rule right here. Okay, so then we prove this actually proves that it's not in any row that is n minus 2 or less. Yeah. So we've proven it all. We've proven it all. That these two were very easy to show, and then this one we just proved that n squared minus 2n is not in any earlier row. There we go.